Dear students, hope all you are enjoying my online classes and getting yourself enriched with the contents of the lectures. So we were on acid-base theory, already discussed 5 theories on acidity and basicity. Now our today's topic is the 6th concept on acidity and basicity, which is the Usanovich concept. So the definition of the Usanovich concept, according to this theory, is an acid is any chemical species which reacts with bases, which can give up cations or accepts anions or electrons, and conversely a base is any chemical species which reacts with acids, gives up anions or electrons, or combines with cations. That means the species which reacts with base is an acid. The species which can give up cation or accept anion is an acid. Which can accept electrons, this is also an acid. On the other hand, the species which reacts with acid is a base. The species which releases an anion is a base. The species which can release an electron is a base, or the species which combines with the cations, that means reacts with a cation, which is capable to react with a cation, is also considered as a base. So what are the features of this concept? The features of this concept are: the Usanovich definition includes all reactions of Lewis acids and bases and extends this concept by removing the restriction that the donation or acceptance of electrons be as shared pairs. That means not only the electrons be a pair, but also it can be a single electron. And this theory considered the general trend of acid-base character in the periodic table and the aspects of coordination. Now, these two things, the general trend of acid-base character in the periodic table and the aspects of the coordination, should be more elaborately discussed. So, on having more elaboration on these two things, let's go through some periodic properties of acidity and basicity. This will discuss the general trend of acidity and basicity along a periodic table. So acidic character from left to right, that is along a period from left to right, increases in the periodic table. In the left hand side you will find sodium, its atomic number is 11, it's alkali metal, and in the right hand side the halogen, chlorine, and their corresponding oxides, sodium oxide and perchloric oxide. Sodium oxide is strongly basic while perchloric oxide is strongly acidic. So acidity increases from left to right. On the other hand, acidic character on descending a group from top to bottom definitely decreases. Such as in this example, in the group 15, the group of nitrogen, phosphorus, arsenic, antimony, bismuth. So arsenic is above antimony. So the oxide of arsenic is more acidic than the corresponding oxide of antimony. Now, if the element is same, then more acidity arises from higher valence characteristics. That is, the higher valence of an element is associated with greater acidic character. We have stannic sulfide and stannous sulfide. So definitely stannic sulfide should be more acidic than stannous sulfide. Similarly, stannic chloride SnCl4 should be more acidic than SnCl2, and sulfur trioxide should be more acidic than sulfur dioxide. So there are lots of examples. Next, high charge of cations favors acidic property. Now look, sodium and aluminium. This is in the first period, in the first group of the periodic table, and this is in the third group of the periodic table. Okay, and their corresponding oxides are sodium oxide and aluminium oxide. This is known as also alumina. Now oxygen is common here, but the charge of the cation here is +1 and here is +3. So naturally +3 charge should be more acidic than +1 charge. Definitely this explains why alumina is more acidic than sodium oxide. And on the other hand, high charge of anions promote basic property. Let's take the example of sodium oxide and sodium chloride. Sodium is common, so the uncommon ions are the anions. Here the oxide anion and here the chloride anion. So oxide has 2 negative ions and chloride has 1 negative ion. So oxide should be more basic than chloride. So Na2O should be more basic than NaCl. Now the aspect of coordination. The term coordinational unsaturation was used to mean the tendency of an atom to increase its covalence. That means if it is unsaturated coordinatingly, then it should have the tendency to accept the anions. Thus the sulfur atom in SO2 molecule is coordinatingly unsaturated. Definitely it has empty d orbitals, so it is coordinatingly unsaturated. As such, SO2 can accept an anion like O2, okay, and then after accepting the oxide, it is forming the sulfide ion. Thus SO2 acts as an acid. Now some fact can be discussed on the basis of this theory. That when a Lewis base or an electron pair donor combines with a Lewis acid, that is an electron pair acceptor, it forms an adduct, which is single molecule. Okay. Now after formation of the bond between the acid and the base, this bond as discussed in the earlier class, thus there is some covalent bond formed with high polarity. That means it has some ionic character. The nitrogen is positively partially charged while boron is negatively partially charged. Now after formation of this bond, there is change in the adjacent bond lengths. That means there is boron and fluorine, so the bond length between boron and fluorine changes. Okay, let's see the example. Here you find that this is the BF3 molecule, which has the boron fluorine bond distance 130 picometer. Picometer is 10 to the power minus 12 meter. Now if it reacts with ammonia, conversely with trimethylamine, then two different adducts are formed. One is NH3 BF3, another is CH3 whole thrice N BF3. Now the bond distance of the B bond F increases. The adduct is more powerful, then more lengthening of the bond. On the other hand, the bond distance between the acid and base molecule, the bond, that is the bond between nitrogen and boron, this bond gets shortened on stronger adduct formation. Okay, thus the B bond F distance increases when the boron atom forms an adduct with ammonia. The distance increases further when a stronger adduct is formed by trimethylamine. That means the nitrogen boron bond distance decreases. It was 160 picometer, it has decreased by 2 picometer here. So there should be some explanation of this, what is happening. So there is the Guttmans rule on the acid base adducts. What is the rule? The stronger and shorter the bond formed in an adduct. That means shorter bonds means the nitrogen boron bond. Okay, this is stronger and shorter. In case of trimethylamine becomes more stronger, and so the nitrogen boron bond becomes more shorter. Now the greater will be the lengthening of the adjacent bond. Adjacent bond means boron fluorine bond. So this bond length becomes elongated, and so this rule is known as the Guttmans rule. So I repeat here, the stronger and shorter the bond formed in an adduct between a Lewis acid and a Lewis base, the greater will be the lengthening of the adjacent bonds in both the donors and acceptor molecules. In both molecules this will happen. Okay, so what are the basis of such phenomena? How were this lengthening and shortening has been discussed. The bond formed in the adduct displaces electron density from the donor atom in the base to the acceptor atom in the acid. The donor atom is nitrogen here and the acceptor atom is boron here. So definitely electron shifts from nitrogen to boron. The donor atom acquires less partial negative charge. Definitely the donor atom is releasing some electron, so its partial negativity in its charge will be decreased. On the other hand, the acceptor atom becomes less positive because it is accepting some electron, so its positivity will decrease. Both these effects reduce the polarity in the bonds in the acids and base molecules, ultimately leading to their lengthening. That means after that, after the adduct is formed, the polarity of the adjacent bond decreases. As a result, the bond lengths increase. Another factor is that the bond lengths increase with increase in coordination number. Boron initially had three atoms attached with it. Now it is bonded with 4 atoms. So this is another factor to increase its bond length. We shall come back with a lot of examples in my next lecture, where the characteristics of the bond length will be discussed more widely. So I would like to conclude my today's lecture here. That's all for today. Thank you.